This film is the case study of one particular concept for a lunar roving vehicle. No claim is made that the concept evolved is the optimum for a lunar rover. It is presented instead to demonstrate how the methods of soil vehicle mechanics are applied to a problem and produce a promising solution. Choice of one vehicle configuration over another results from a study of each vehicle type in a given terrain. Here, a screw-type vehicle is shown in a soil bin. In certain soils and under certain conditions, a three-axled vehicle with large wheels, such as this one, might prove to be a more successful type. Or, under special terrain conditions, an articulated tracked vehicle might be the best choice. In any case, use of scale models is a key technique. Investigation of the soil's mechanical properties is a companion step in analysis of vehicle performance. This instrument is measuring the vertical stress-strain properties of the soil by forcing a plunger under load into the sample. Data on the horizontal stress-strain properties of the soil are obtained by turning this shear ring under load. This information will be used to predict vehicle sinkage and hence motion resistance and vehicle thrust. In the event that lunar soil is not soft and powdery, tests are also run on gravelly and hard soils. The vehicle scale models are then placed in a bin containing soil of known properties. Here, the soil is intended to simulate the lunar surface. Planned undulations and irregularities are introduced into the terrain and the vehicle mobility evaluated. If the soil was so weak that it could not support the weight of a lunar rover, the vehicle might be designed like this Archimedean screw, which burrows through the very light and fluffy soil and achieves an adequate degree of mobility. Finally, studies based upon various possibilities for lunar soil indicated that an articulated, wheeled vehicle offered many promising advantages. It demonstrated a high degree of overall mobility and had the advantage of being simple and reliable. Because of uncertainty regarding lunar terrain, tests were performed under conditions that included extremely rough terrain characterized by large obstacles. The model, consisting of 6 large light wheels, all motor-driven, coupled by a flexible frame, showed excellent small-scale results and was selected for further development. A large-scale vehicle was built and a laboratory test run over a step obstacle 5 feet high. It demonstrated the obstacle crossing ability of the test vehicle, derived in great measure from the extreme flexibility of the frame. The test bed vehicle is 12 feet long, 5 feet wide, with 3-foot wheels. The flexible frame is built of 6 parallel spring steel bars, which allow for considerable freedom of pitch and roll. By contrast, when a rigid frame was added to simulate a more conventional vehicle, it was totally unable to surmount the test obstacle. A vehicle of the rigid type is capable only of climbing an obstacle approximately equal to its wheel radius. Each wheel is powered by an individual drive motor. The wheel rim is supported on and rotates around 3 small rollers mounted on the axle frame. Simultaneous steering is accomplished on both the front and rear units by a small motor-driven worm gear reduction. Steering is of the wagon type with a maximum steering angle of 45 degrees and a resulting turn radius of 9 feet. Upon completion of the laboratory tests, a series of field tests was planned. Terrains were selected to simulate possible lunar surface conditions. According to many investigators, one strong likelihood for the moon is a terrain consisting of dry, loose, granular material. Here, simulated by a very loose, wind-blown sand. When disturbed, this sand flows in an almost fluid manner until it assumes a natural slope, known as the angle of repose, in this case forming dunes of about 33 degrees maximum slope.